Hello everyone. Today we are going to analyze this beam using moment distribution method. Before analyzing, let us see the beam one time. In this beam, there are two spans, span BC and span CD. There is also an overhanging span AB. In the overhanging span, there is uniformly distributed load 12 kN per meter acting for the full span. In the span BC, there is a point load 48 kN. It is acting in the center of the span. In the span CD, there is a uniformly varying load. It varies from 0 in the point C to 90 in the point D. In the points B and C, there are hinged supports. In the point D, there is a fixed support. The overhanging span is 3 meter long. The span BC is 6 meter long. Span CD is 4 meter long. In this analysis, we have to find 5 moments. In the joints, there will be 2 moments. In the joint B, there are 2 moments, MBA and MBC. In the joint C also, there are 2 moments, MCB and MCD. In the fixed support, there will be a moment. In the point D, there is a fixed support. Here, we have the moment MDC. So, totally, we have to find 5 moments. Also, we have to calculate 3 reactions RB, RC and RD. In the joint B, we can easily calculate the moments because on the left of B, there is overhanging. To find MBA, we have to calculate the moment in the point B from the point A. In the overhanging span, there is a UDL 12 kN per meter. The length of overhanging is 3. Now let us calculate the moment in the point B due to the load 12 kN per meter. For that, we have to multiply this load with the distance and distance by 2. Here the distance is 3, so we are multiplying with 3 and 3 by 2. In this way, we are getting MBA, which is equal to 54 kN meter. The values of MBA and MBC will be same, but they will have the different signs. MBA is acting in the clockwise direction, so it will be positive. MBC is acting in the anti-clockwise direction, so it should be negative. But both of the values are same. To calculate MBC, we have to just change the sign of MBA. When we do that, we are getting minus 54 kN meter. Now let us calculate the fixed end moments. First, let us calculate the fixed end moments in the span BC. In the span BC, there is a point load 48 kN. It is acting on the center. The formulas to calculate the fixed end moments are minus WL upon 8 and positive WL upon 8. In the formulas, let us apply the values. W is 48, L is 6. After applying the values inside the formulas, we are getting M of BC and M of CB. Now let us calculate the fixed end moments in the span CD. In the span CD, there is uniformly varying load. It varies from 0 in the point C to 90 in the point D. The formulas for the fixed end moments are minus WL square upon 30 and WL square upon 20. Let us apply the values inside the formulas. W is 90, L is 4. After applying the values inside the formulas, we are getting m of CD and m of DC. In the moment distribution method, we have to find the distribution factor. We have to calculate the distribution factor only in the joints. In this analysis, there are two joints, joint B and joint C. No need to calculate the distribution factor in the joint B and waste the time, because we can easily say the distribution factor in the joint B since there is overhanging on the left of B. For the overhanging side, the distribution factor will be 0 and on the other side it will be 1. So the distribution factor for BA will be 0 and for BC it will be 1. In this case, we have to calculate the distribution factor only in the joint C. To calculate the distribution factor, we need to find the stiffness. Let us see the formulas to calculate stiffness. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged or with roller support, the formula is 3EI upon L. If the fair end is continuous, the formula is 4EI upon L. In the joint C, first let us calculate the stiffness for CB. For that, from the joint C, we have to look at the point B. In the point B, there is a hinged support. If the fair end is hinged, the formula for stiffness is 3EI upon L. Length of CB is 6. Let us apply that. Finally, for the stiffness of CB, we are getting 0.5 EI. Now let us calculate the stiffness for CD. For that, from the joint C, we have to look at the point D. In the point D, there is a fixed support. If the fair end is fixed, the formula for stiffness is 4EI upon L. Here, length of CD is 4. Let us apply that. Finally, for the stiffness of CD, we are getting EI. When we calculate the stiffness for CB, we must be very careful. We should not consider the point B as continuous because there is only overhanging on the left of B. In this case, we should not consider the point B as continuous. That is why I have applied the formula 3EI upon L. Now let us calculate sigma k. For that, we have to add these two values. After adding, we are getting 1.5 EI. Now let us calculate the distribution factor. The formula is k upon sigma k. Using the formula, we can calculate the distribution factor for CB and CD. Now let us start making the moment distribution table. In the table, first let us enter all of the members. Then let us enter the distribution factor values. In the overhanging end, the distribution factor will be 0. So for AB, it is 0. We already know the distribution factor for BA is 0 and for BC it is 1. In the joint C, we have calculated two distribution factor values. Let us apply them. In the fixed end, the distribution factor will be 0. So for DC, it is 0. Now let us enter the fixed end moments. In the span BC, we have calculated two fixed end moments. Let us apply them. Also, in the span CD, we have calculated two fixed end moments. Let us apply them. We have already calculated the final moment for MBA, that is 54 kN meter. For BA, let us apply that. We have also calculated the final moment for BC, MBC, which is equal to minus 54 kN meter. So in the table, we have to make BC minus 54. The fixed end moment for BC is minus 36. When we add minus 18 with this minus 36, we will get minus 54. So we have released BC. Now we have to give carryover from BC to CB. When we divide minus 18 by 2, we will get minus 9. Now let us calculate the adjusted fixed end moments. For CB, we have to add these two values. After adding, we are getting 27. For CD and DC, there are no changes. Now let us make the first distribution. We know that the distribution can be done only in the joints. Here there are two joints, joint B and joint C. We should not make any distribution under the joint B because we have already calculated the final moments for BA and for BC. In this case, we can make the distribution only in the joint C. First, let us make the distribution for CB. For that, we have to add these two fixed end moments. Then we have to multiply with the distribution factor at CB. When we do that, we are getting a negative value. So we are entering inside the table as positive. Now let us do the distribution for CD. For that, we have to add these two values, then multiply with the distribution factor at CD. When we do that, here also we are getting a negative value. So we are entering inside the table as positive. Now let us do the carryover. We cannot make the carryover between BC and CB because we have already released BC and found the final moment. In this case, we can make the carryover only between CD and DC. For DC, there is no distribution, so we cannot make the carryover. For CD, the distribution is 14. When we divide 14 by 2, we will get 7. In this problem, we cannot continue further. We know that we can make the distribution only in the joint C. In the joint C, now there are no values. So we can't make the next distribution. In this case, let us add the values and find the final moments. When we add these two values, we are getting 34. When we add these two values, we are getting minus 34. When we add 72 and 7, we are getting 79. So in this analysis, we have calculated all of the final moments. In this analysis, we have calculated all of the moments. Now we are going to find the vertical reactions. Let us take the overhanging span AB and the span BC together and calculate the vertical reactions. When we take them together, no need to consider MBA and MBC, they will get eliminated. We have to consider only one moment, that is MCB, which is acting in the clockwise direction. In these spans, first I am going to find RB. For that, I am going to take moment about C. In this case, I am moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. This UDL 12 kN per meter is acting towards the point C in the anti-clockwise direction. So it will be negative. The distance is 3. So minus 12 into 3. Then for the UDL, we have to find the centroid distance. Here the distance is 3. So the distance 3 by 2. We are taking moment about C. So we have to take this distance also. This distance is 6. So we have to add 6. RB is acting towards the point C in the clockwise direction. So it will be positive and the distance is 6. So 6 RB. The point load 48 kN is acting towards the point C in the anti-clockwise direction. So it will be negative and the distance is 3. Then we have a movement. This movement is acting in the clockwise direction. So it will be positive. After the calculations, we are getting RB, which is equal to 63.33 kilonewton. Now let us apply the rule sigma V is equal to 0. Using the rule, we can calculate RC1, which is equal to 20.67 kilonewton. Now let us take the span CD and calculate the vertical reactions. In the span CD, there are two movements, MCD, which is acting in the anti-clockwise direction, and MDC, which is acting in the clockwise direction. In this span, first I am going to calculate RC2. For that, I am going to take moment about D. RC2 is acting towards the point D in the clockwise direction, so it will be positive and the distance is 4. So for RC2, this UVL is acting towards the point D in the anti-clockwise direction, so it will be negative. For this UVL, we have to multiply the area with the centroid distance. We know the area formula of a triangle, half into breadth into height. Here the breadth is 4, height is 90. Using the values, we can calculate the area. Now we have to find the centroid distance. We are taking moment about D. In this case, we are moving towards the right hand side. For this triangle, the centroid distance towards the right is 1 upon 3 into breadth. Here the breadth is 4, so 1 upon 3 into 4. Then we have two movements. 34 movement is acting in the anti-clockwise direction, so it will be negative. 79 movement is acting in the clockwise direction, so it will be positive. Finally, we are getting RC2, which is equal to 48.75 kilonewton. Now let us apply the rule sigma V is equal to 0. RC2 and RD are acting upwards, so both of them will be positive. The UVL is acting downwards, so it will be negative. To calculate the total load from this UVL, we have to find the area. We know the area formula, half into breadth into height. Using the formula, we are getting the total load 180. 180 minus RC2, we will get RD. Now let us add RC1 and RC2. After adding, we are getting RC. Now let us calculate the shear force values. I am going to start in the point A and move towards the point D. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. You can see the shear force calculations. Using the shear force values, we can make the shear force diagram. Under the UVL, we have to make the shear force diagram in the shape of parabola. Now let us draw the free movement diagram. To draw this diagram, we have to consider every span as a separate simply supported beam. In the free movement diagram, no need to consider the overhanging span. In the span BC, there is a point load 48 kilonewton. It is acting in the center. The formula to calculate the maximum bending moment is WL upon 4. Here W is 48, L is 6. When we apply the values inside the formula, we are getting 36. Using that, we can make this diagram. In the span CD, there is uniformly varying load. It varies from 0 in the point C and to 90 in the point D. The formula to calculate the maximum bending moment is WL square upon 9 root 3. In the formula, let us apply the values. W is 90, L is 4. When we apply the values inside the formula, we are getting 92.37 kilonewton meter. This maximum bending moment occurs at L upon root 3. Here L is 4. So it occurs at 2.31 meter. from the point C. For the UVL, the bending moment diagram should be in the shape of parabola. Now, using the end moments, we can make the end moment diagram. Then we have to combine the end moment diagram and free moment diagram so that we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.